Hey there, chemistry team. Ready for video number 12. So close to the end, it itches. All right. This is part 2 of our titration of a weak base solution with a strong acid solution as the titrant. Just so many calculations because I'm hitting every part of these titration curves. You should be able to handle everything after these crazy videos. We're going through the full meal deal for you guys. All right, we did, in part 1, we did the titrant volume at the equivalence point, so you could see where the pre-equivalence and post-equivalence regions were. We did the initial pH of the weak base, the trimethylamine, with the ice table. We did 2 in the pre-equivalence region, right? We did the about less than a milliliter away from the equivalence point there, using the buffer for weak bases, the Henderson-Hasselbalch equation. That was quite involved. And then we did the really easy half equivalence point, the halfway mark, where the POH was equal to the PKB. That was easy. So now let's do one of the two toughies, right? So the buffer region, the pre-equivalence region, other than the half equivalence point, is a lot of work. The equivalence point is also a lot of work because when you're titrating a weak acid or a weak base, the resulting products you get are not neutral. They are with strong acid, strong base, but if you've got a weak base or weak acid, if you're titrating weak acid like we did a while ago, that conjugate base that you form is going to ionize in water. So at the equivalence point, it's not a pH 7, it's a pH greater than 7. This is just the opposite. Okay? We are starting with our weak base, right, our trimethylamine, adding the strong acid, the hydrochloric acid, so we're going to get the trimethylammonium ion, the conjugate acid of the weak base, plus the chloride ion. Now, the chloride ion comes from a strong acid, so that's neutral. Right? So the stronger the acid, the weaker its conjugate base. So chloride ion, its a conjugate base, is so weak it won't even ionize in water. So heck with the chloride, fortunately. But this trimethylammonium ion, that little booger there, that's a weak conjugate acid. Yikes! All right, so at the equivalence point, all of the original weak base is toast. Bye-bye. All of the added strong acid titrant is gone. Bye-bye, right? Equivalent amounts. They neutralize each other. And we found that in lab with the indicator with the faintest color possible. And that's neutral. So the only species that dominates that we have to worry about is that conjugate acid, that trimethylammonium ion. Would that make sense, since it's a weak conjugate acid, that the pH will be less than 7 at the equivalence point, right? Kind of the opposite of what we did when we titrated a weak acid. The conjugate base gave a pH greater than 7 at the equivalence point. So this should be less than 7. How much less than 7? We don't know. It's not a strong acid. It's probably not going to be down, in the 2 range or anything like that. But we should. So if we get an answer that's greater than 7, we screwed up, didn't we? We need to figure out what's the concentration of that trimethylammonium ion. Right? Well, it's going to be base because we didn't start with any, so whatever the millimoles of either one of these is will determine that. So since we were given we've already calculated the original millimoles of the base, right? We did that, I think, in step 2 and a couple other steps. So we already know that value. Well, that'll be the millimoles of this that forms. Figure out the total volume of the base we started with, plus the volume of the acid, which we calculated in part 1, right? The equivalence point volume. Add those together, so just take the millimoles of that form divided by the total volume from the dilution, and you got the concentration. Hey, then you just set up an ice table like any weak acid. You're going to look on your weak acid Ka tables and not find the Ka value. Oh, darn schnucks. I can't find it, so you got to use that Kw as Ka times Kb to figure it out. No big deal. Set up your ice table, solve for X. X is going to be H3O plus. Take the negative log. You've got it. Hopefully I'm making it sound real simple, but when you do it, you're like, oh, my brain! And when you're on a test, you're like, my brain's gone! Right? So let's go through. I'll walk you through the steps. This is no different than when we did a weak acid with a strong base titration. Just we're using KBs instead of KAs, and everything's flipped around. So let's figure out the concentration of our conjugate acid formed at equilibrium. Let me write up a new board. Hopefully you figured out the concentration of the trimethylammonium ion at the equivalence point, which will form an equilibrium, right? So let's do the stoichiometry. Do the neutralization first, then we'll do the equilibrium. Or neutralization always first. We got to figure out how much are we starting with, how much is left after it's all done. So obviously, we're not going to have any of the original base or acid added left. They're gone. That's the equivalence point. So we're only going to have these. We're not worried about the chloride. We're only worried about the methylammonium ion as the conjugate acid. And you could have skipped this, right? You could have kind of done this in your head, but I'm just bringing you back when we looked at the first couple problems. We had 27.52 milliliters of our trimethylamine base solution times its concentration of 1.39 millimoles per milliliter. And then 1 millimole of that weak base will form 1 millimole of the conjugate acid. You can see it from the stoichiometry. So we just get 38.252 millimoles of the conjugate acid formed. That's good to 3 significant figures. Now, we had already calculated the millimoles of base. You could have just brought that answer from before and understood the 1-to-1 ratio. So you literally could just immediately skip this problem and just went 38.252 millimoles of methylammonium, trimethylammonium ion, due to 1-to-1 mole ratio with the base. Right? So that's technically, these are both limiting reactants. You could use either one. The total volume at the equivalence point will be the 27.52 milliliters of the original base solution, given to you in the original problem, plus the 25.501 milliliters. That was calculated in step 1. That was the volume at the equivalence point. Okay? Add those together. That's good to 2 decimal places. That's good to 1. So we get 53.021 milliliters, good to 1 decimal place. So now the concentration is just the millimoles divided by the milliliters. Millimoles per milliliter is the same as moles per liter. It gives you concentration and molarity. So 38.252 millimoles to 3 significant digits divided by 53.021 milliliters to 3 significant digits. We get 3 significant digits in our answer. So 0.72144 molar. Good to 3 significant digits. No need to round that because we're not really asking for it. We're asking for the pH. So we don't round anything until we get the pH. All righty. So now we know our initial concentration. Go ahead and set up an ice table for this conjugate acid ionizing in water because now we're at the equivalence point. This is the only major dominant species present that interacts with water. There's a lot of chloride, but we're not worried about the chloride ion. It's neutral. So set up an ice table for that, ionizing in water, producing the hydronium ion and its conjugate base. And let's figure out what X is. Go for it. How's your ice table looking? All right, we've got our conjugate acid, our trimethylammonium ion, ionizing with water. This is happening at the equivalence point. Can't see it with our pathetic human eyeballs, but that's what's happening in your Erlenmeyer flask when you're titrating things in the lab. Not that we'd have you titrate a weak base in lab. I never assigned that. We always titrate an acid with a strong base, but we could theoretically. So that's an acid, so that's going to donate an H+, so that gives you the hydronium ion. And you lose the H+, so you're back to the original trimethylamine. All right, just not a lot. This is a weak acid, so there's going to be just a pathetically small amount of that trimethylamine. All right, Q obviously is 0, so that's going to be less than K. It's going to shift to the right, so we're going to have negative X's here, positive X's is there. Broken record, broken record, broken record. So we're going to lose X of the trimethylammonium conjugate acid. And we're going to form X of that and X of that. So take the initial plus the change. So at equilibrium, we're going to have the initial concentration, 0.72144 minus X. Right? And that's the concentration we calculated after neutralization. 0 plus X is X. 0 plus X is X. Patterns, patterns, patterns. That's what makes tests easier. Repetition, so you just feel comfortable on the exam, just like if you're in sports. You practice, 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 practice. Becomes routine, muscle memory. So when it's tournament championship game, it's just instinct. Just everything's instinct. Your motions, your throwing, your hitting, pitching, everything. You're not thinking about it. It's just happening. That's where you want to be when you're taking exams. Right? Quizzes are like scrimmage games, but major exams, you should be so mentally instinctive at that point and confident coming in, the psychology of an exam. You come in, you recognize the problem, boom, 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 boom. Right? You go, hey, this is an equivalence point pH. Let's do the neutralization. What's left at the equivalence point? We just have that one conjugate base or conjugate acid. Calculate its concentration using neutralization stoichiometry. Once we have that number there, plug it in the ice table. Just routine, routine, routine. Let's set some things up. You ready? we can set up the Ka for that, correct? Let's do it. So this is a lot like when we calculated the initial pH. It's just the initial pH was for a weak base, equivalence points for a weak acid. So Ka is going to be the product concentration. So that'll be the concentration of the methylamine raised to the power of 1. That's why I love acid base. All the stoichiometric coefficients are 1. Ha ha! Makes for really nice Ka and Kb expressions. We've got the hydronium ion over there, raised to the power of 1. And in our denominator are our reactants. So we're going to have the trimethyl ammonium ion concentration raised to the power of 1. And water's a liquid, so we don't worry about it. Let's plug in our equilibrium values from our ice table. So the trimethylamine will be X. Hydronium ion will be X. Been there, done that. Oop, it's another hit. Your shortstop, poop, poop, poop. Throw them out at first base. Automatic. It's routine, right? Or it's a bunt. Bunt, bunt, bunt. Your third base, you're charging, you pick it up, throw them out. Boom! Really nice, huh? So this will be 0.72144 minus X. That is one ugly line right there. So we're just bringing that down. To avoid the nasty quadratic equation, let's assume X is tiny, right? So 0.72144 minus X would be approximately 0.72144. So X times X is X squared. We good with that approximation right there? We have to prove that our assumption is valid. So either solve for X, divide that by the initial concentration, times it by 100, and make sure that's less than 5%. Or take the concentration, 0.72144, divided by the Ka value. There's a problem. We don't know the Ka value. Oh, correct monkeys. What are we supposed to do? So if you're looking for the Ka value, get your Ka table. You're not going to find anything really that weird on here. Right, do you see anything like that? Take a look on there. Trust me, you're not going to find it. Not there. Not there. So sorry. Take a number. And whenever you have that oh crap moment on an exam, oh crap, I can't find it on the table. Instead of raising your hand going, oh, professor, I can't find it on the table. And then I'll sit down and go, it's not supposed to be on the table. And then you go, well, I don't know. I go, there's a way to figure it out like we did in lecture. And your homework's over and over and over. Remember, if you can't find it on the table, use the KW. Is Ka times Kb, right? I don't know the Ka. So the Ka for that will just be Kw over the Kb of the conjugate you form, right? So Kw, if you don't remember, right, I'll give that to you on an exam. So that's 1.00 times 10 to the minus 14. Kb for that, we have, I mean, you've done it, used it several times already, but you could always, if you panic or something, just go back to your base table. Remember the Kb, 6.3 times 10 to minus 5. Right there. So 6.3. That, whoa, I almost lost a pen there. Looks like that's going to be a very large number. You ready? So let's take 1.00 second function, EE. I can barely read that, to the negative 14, divided by 6.3 second function, EE, negative 5. Looks like we're good to two significant digits. I get 1.587 times 10 to minus 10. 1.587 times 10 to the minus 10. All right, so that is the Ka value for that, which was not on the table. That's pretty easy to find, and I'll give you this equation. I'll give you Kw. It should be easy. You just have to know, oh, I can't find it. Immediately go, boom, this is how you calculate it. Bam, bam. 30 seconds later, you got it. So I've run out of room. Go ahead and test this assumption for me. So take the concentration of the acid divided by the Ka. Make sure that's bigger than 100. That means our assumption here that X is tiny is valid. And then solve for X. So X will just be the square root of Ka that we just solved for times the initial concentration. Boom! We're almost there. Go ahead and do it while I erase my board. Was your assumption valid? So I rewrote our K expression, which is approximately x squared over the initial concentration. And we calculated that out using the KW expression. So molarity, 0.72144 to 3 significant digits, divided by Ka, 1.587 times 10 minus 10, good to 2 significant digits, will leave us with 2 significant digits. I get 4.545 times 10 to the 9th, good to 2 sig figs. That's a lot bigger than 100, so I'd say yes, we are valid in assuming that x is tiny, and 0.72144 minus x is approximately 0.72144. That now allows us to calculate, so we can now bring this down. So x squared will be Ka times that. Right? So if we take Ka times the original concentration, that would be x squared, then we square root both sides. Boom! Just like that. Let's plug in Ka. So that'll be 1.587 times 10 to the minus 10 times the original concentration, 0.72144, and let's take the square root of that whole shebang. So x will be equal to that times that. Take that answer, take the square root, good to 2 significant digits. We're limited in the Ka value. Oh, fumbled my pen. So much for my favorite colored pen. I love purple. Calculate that for me, and I want you to finish this problem before I do. I'll pause it and let you attack it. Calculate x. What is x equivalent to? Look at your ice table. What does x mean? It is equal to 2 different species on your x table at equilibrium. We're interested in one of those to extract the pH out of. See if you can do that for me. I'm going to pause, take a sip of my favorite beverage. If you're my student, you know what this beverage is. Did you get 4.97 for your pH? I hope, because that's what I hope you get on the exam. Hopefully you get what I get. Unless I screw up my own exam and post up the exam answer key and I get 57 emails saying, Professor, I got a different answer than you. And I'm like, oh, that happens sometimes. All right, so Ka times the initial, multiply those together, take the square root, I get 1.069 times 10 minus 5th molar. That's x, and from the ice table, that is hydronium ion concentration. Yay! So now let's just take the negative log of that. So the negative log of 1.069 times 10 minus 5. We have 2 significant digits in the log term, which means we'll get 2 decimal places in our answer. 4.9710 rounded to 2 decimal places leaves you at 4.97. Does that make sense? Well, we have a weak acid, right? That's the only species present in equilibrium. It's not a strong acid, so it's not going to be, probably strong acids are down below 3-ish. Weak acids are usually above 3, give or take. Depends on the concentration and all that, and the Ka value, of course. Some weak acids are not as weak as you would think, and some are pathetically weak, right? A 10 to the minus 4 is different than a 10 to the minus 9, right? So 4.97, that's less than 7. That's in the acidic range. Makes sense for a weak acid, all right? We're good to go there. That gives us a key data point in our titration curve at the equivalence, where that steep rise is, that 4.97 is right in the middle. That'll allow us to find out what indicator we should pick. We got one more. Let's do a post, just one post. Ideally, if we had time, we do 2 data points past the equivalence point, one butting right up against within a milliliter of the equivalence point, and then one way maybe 20, 25 milliliters past, so we can see the end of the S, or in this case, the mirror image of the S, because we're titrating a base. But let's do one within 1 milliliter or so of the equivalence point, so we can see where that, the beginning of that steep rise for acids and drop for bases is, so we can make that proper S. All right, let me erase this board, do one last problem. Here we go, post-equivalence point region, my friends. So that's anything past the volume of titrant that we needed to get to the equivalence point, which we calculated in step 1, right? That keeps coming back to haunt us. That's why I always do that first. So that was like 25.501 milliliters, I think, to hit the equivalence point. So anything past that is the post-equivalence region, and all calculations are identical at that point. All right? So let's just say 26.00 mils, and that's how I would ask it on a test. What would be the pH after adding 26.00 milliliters of the titrant, right? We got the strong acid titrant. This is purely just a neutralization stoichiometry problem. No buffers, right? We don't have to worry about anything ionizing in water, nothing like that. So this is one of the easiest regions to do. Because all the original weak base, because we started with that weak base in that Erlenmeyer flask, boom, it's toast. We added more acid, a titrant acid, than the base. So we will have leftover strong acid titrant and all the weak base is gone. So if you do the neutralization stoichiometry, take the amount of acid you added, the millimoles of acid added, subtract the amount of base that it neutralized, you'll have a residual amount. So the base is the limiting reactant. You'll have a leftover residual millimoles of your strong acid. Divide that by the total volume of the acid and base, and that gives you the concentration of that strong acid, in this case hydrochloric acid, left over. It's a strong acid. We can make some really nice simplifying assumptions because it's a strong acid. Yes, you're going to have, in this case, the trimethylammonium ion present, like we did at the equivalence point, right? But at the equivalence point, that was the only dominant species. But past the equivalence point, you have leftover strong acid and the conjugate acid, the trimethylammonium ion that formed. But remember, whenever you have a strong acid with a weak acid, the contribution of hydronium ion from the strong acid so dominates everything else, you can just ignore any contribution from the conjugate acid that's present. Just forget it. It's nothing. It's way out to the decimal places that are irrelevant for significant digits. And we can ignore any hydronium ion present from water autoionization. The only time we have to worry about water autoionization is at the equivalence point for strong acid, strong bases, because there's nothing left. It's just all of the ions formed, the acid's gone, the base is gone, all of the ions formed a neutral. So the only thing even contributing to H3O plus would be the water autoionization. But we can ignore both of those factors. If you forgot about that, go back to one of the first videos from this chapter. And so we know the concentration of the HCl, which is the concentration of H3O plus. Wada bing, wada boom, baby. Take the negative log. Done. You are safe at first. And then they overthrow first and you steal second. I miss coaching so much. All right, here we go. Let's do it. See if you can. So while I've been talking, those of you who have had me for live lectures know I just keep talking, expecting you to do the problem. Right? So hopefully you're done with the problem already. Go for it. Do the neutralization stoichiometry for me. All right, I'm piecemealing this for you, gang. Here's our neutralization equation again. So all of this is going to be gone. We're going to have leftover strong acid titrant. We're going to ignore the conjugate acid formed, any contribution of hydronium from that, and the chloride's neutral. Here we go. Initially, we have 38.252 millimoles, good to 3 significant figures, of the base. And that was calculated back in part 3, really in part 2, but specifically in part 3. So you can just bring that from before. No need in recalculating it. Well, how many millimoles of the strong acid titrant did we add? Well, you take the volume times concentration. So 26.00 milliliters, or whatever I gave you, of the solution. And the concentration provided in the original problem was 1.50 molars. So that's 1.50 millimoles of HCl solute per milliliter solution. Milliliters of solution cancels out. Good to 3 significant digits. I get 39.000. Not that you need all those trailing zeros. You could just say 39.0 millimoles of HCl. Notice there's more acid than base. So in this case, the base is the limiting reactant, but that really doesn't matter. But we need to figure out how much of the HCl is left over. So how many millimoles of HCl is left over? Just subtract the two. It's that easy. And then figure out the total volume, acid plus base. Calculate the concentration of the HCl left over after neutralization. Take the negative log and get the pH. See if you get what I got. You can do it. Hopefully you can do it now because you're going to have to do it on the test. Ha ha ha. So take the 39.0 millimoles of acid we added, subtract the 38.252 millimoles of base originally, more acid than base, so the difference is the amount of acid left over. 1 decimal point, 1 decimal point. So to 1 decimal point, tracking uncertainty, I get 0.748 millimoles of HCl left after it obliterated all of the base. Well, what's the total volume? Well, originally we had 27.52 milliliters of our trimethylamine weak base. That never changes. That's the same. And poured that in before we did anything in the lab. We added 26.00 milliliters from the burette. Not that you would do that in reality, because you don't go past the endpoint on purpose. Add those two together, both good to 2 decimal places. I get 53.52 milliliters of solution total. So just take the millimoles of HCl divided by the volume of solution. I've run out of room on my board, so I have to pause and rewrite this. Take the concentration, get the pH for me. There we go. Take the millimoles, 0.748, good to 1 sig fig, divided by the total volume, 53.52, good to 4 sig figs, limited to 1. Gives us 0.0139 molar hydrochloric acid, good to 1 significant figure. That's what's present, and we're ignoring any H3O plus contribution from water ionization, anything from the conjugate acid form. It's the strong acid. It dominates the H3O plus production. Since it's a strong acid, 100% ionization, so the HCl concentration is the hydronium ion concentration, 0.0139. Let's take the negative log of that, right? Negative log of hydronium is the pH. Since we have 1 significant digit in our log term, we'll get 1 decimal point in our answer. So the negative log of 0.0139 is 1.856, good to 1 decimal. That rounds up to 1.9. Does that make sense? Yes, it's a strong acid. It should be down in the 2 range. Makes sense. So let's draw our titration curve. See if you can do that for me. Take all the data points and sketch together a curve and pick an indicator for me before I do this. See how you do. Did you do your titration curve? Here we go. It's pretty easy once you've done all these data points. Draw your pH on one side. I just go from here 1 to 12. Just make sure it contains all your values. You don't have to go 0 to 14. And volume of titrant. In this case, my equivalence point was around 25, so I just kind of went 50 mils. Put down your data points. So initially, we were at like 11.97 or something, way up there for a weak base, right? The equivalence point was like a 4.97 at 25.5 milliliters. We did 25 milliliters and got right or close to 8. We did the half equivalence point, which was like a 9.80, and that was at about 12.5 milliliters. And then we did 26 milliliters right after the equivalence point. And that was like just below 2. Right? Ideally, I would have done one here out at like 45 mils so I could see where, but not a lot of room to go. It might have been better if I started this at 0. So now let's just draw our curve. Okay? So we've got the buffer region here. So it kind of drops, hits that buffer, hits that steep drop, and then it just kind of tails off as we go. So you can see that steep region right around that equivalence point. That's characteristic for all of them. So this here is our buffer region right there. That's where we have the leftover weak base and the conjugate acid that forms, all done the same way. This is our post-equivalence region, leftover strong acid. So post-equivalence region. There's our equivalence point. There's our initial pH. So when we're picking an indicator, we want to get within this steep rise. So I'd say right around here to right around there. So that's our indicator region. So I'd say we want to pick an indicator. Now, phenolphthalein wouldn't work for this. Phenolphthaleine's up in this range, right? That would not be a valid indicator for this titration. So I'd say anywhere from 3 to 7, maybe 3 to 6 to be safe. So we just grab our trusty indicators, and we want to go anywhere from about 3, which is here, to say 6 to be safe, something with a 2 pH range. So you're right down in this region right here, maybe methyl red, bromocresol green. Bromocresol green would be fun. Kind of starts yellow. Oh no, it actually starts blue and goes to yellow because we're going backwards. So this will go yellow to red. Not an option for a colorless to a colored one, which is best, but a couple available options. There you go. And if we did a strong base with a strong acid, it would look similar. It's just you would start a little higher and have a much steeper drop here. More choices of indicators. Boom! Done with our monoprotic acids bases. One more video left. We're done with this semester, my friends. We need to do polyprotic species. I'm not going to do any math with it. I just want you to get a feel qualitatively how they look. And we'll do that and be done with the semester. You guys are awesome. Do your homework.